Yeah, hi everyone. Thank you very much for coming. Thanks for to the organizers. Can you hear me? Is this working? Okay. Yeah, I'm going to talk about recent work which I've done together with Rito, actually, which we call probabilistic forecasting with generative networks via scoring rule minimization. And actually, some of the concepts have already been introduced in 2 previous talks, which, well, for which I thank the speakers because they made my job a bit easier. So yeah, I think I'm gonna start, if this works. Yes, by giving a quick overview of generative networks. Yeah, precisely what do I mean by generative network? It's just a way to use, well, it is a way to use neural networks to represent probability distributions. And to be more precise, they are basically defined by like neural network, which I call H phi here, where phi represents the weights of the neural network, and a probability distribution Pz over the space, let's say calligraphic Z, which is the input of the neural network. So this neural network induces distribution, which I will call P phi here, over the output space of the neural network, Y, from which you can basically sample by sampling from the noise space Z, and then just passing the input through the neural network and getting the output. Yeah. So yeah, the idea here is basically we want to train a neural network P phi, generative network P phi, to represent a distribution P star, let's say, from which we only have samples. We cannot evaluate the distribution P star. Yeah, but at the same time, you cannot evaluate the density of P phi either. You can only get samples from it. So this seems to be, well, hard to do. So well, this was traditionally, well, let's say solved by the machine learning community a few years back in 2014 with this kind of groundbreaking paper by Goodfellow, where they introduced the concept of generative adversarial networks. And basically the idea here is we have what I described before, like the generative network or generator for short, and they put it basically in a sort of game against a discriminator network, where basically, let's say the discriminator network has to discriminate between the data which the generator produced and the samples from P star, in this case, these images of famous people, while at the same time the generator has to basically attempt to fool the discriminator in a sense, so basically which boils down to generate images as close as possible to the real ones. Right. Yeah, to be, let's say, a bit more rigorous, this is the loss function which they originally used in this paper. If you have a look at this, there are a few terms. So first of all, SIP psi is a discriminator network, and it basically, well, SIP psi of Y is a value between 0 and 1, which represents the discriminator's probability in Y being true. And in this equation, in this, well, the loss function, basically you have the first term is an expectation over samples from the original data set, so real images in a sense, and where you penalize the logarithm of the probability of the discriminator being, well, the logarithm of the probability that the discriminator gives for this sample being true. And the second term instead is an expectation over samples from your generator network, where you penalize the logarithm of the probability that the discriminator believes the output being fake instead. And well, if you have a look at this, basically the task is solving a maximization problem over the weights of the discriminator, while at the same time solving a minimization problem over the weights of the generator phi. But if you were able to solve this, then you can show that this actually gives you what you want. So if you're able to solve this problem in a sense, then P phi will be equal to P star. Yeah, this seems to be very nice, but it has some problems, as you can imagine, given that you have this min-max problem. This is fairly unstable in general. It is pretty hard to, let's say, do in practice. And you also have to have two neural networks. So hyperparameter tuning is pretty hard. In practice, sometimes this leads to poorly calibrated distributions. Right. So specifically, for instance, for the case of, let's say, probabilistic modeling or probabilistic forecasting, having a poorly calibrated distribution is a big problem in a sense. So we wanted to develop a different training method for generative networks, which improves the calibration of the distribution. So we ended up looking at scoring rules. So a scoring rule is just a function between a distribution, let's say P phi, and an observation Y. And you can think of this as a penalty when you state the distribution P phi for the realization Y. So yeah, if you assume your observation came from a distribution P star instead, then you can define this expected scoring rule, which is just written here down here, and it's basically just taking the expectation over your observation Y from coming from P star. We define the scoring rule here to be strictly proper if the expected scoring rule is uniquely minimized when your P phi, which we can call the forecast distribution in a sense, is equal to P star. So what's an example of scoring rule? It was mentioned already before, but for instance, the energy score is a strictly proper scoring rule. And if you have a look at the energy score, it is basically, it boils down to a couple of expectations inside of which you are computing some distances. And the important bit is that this expectation is over two independent and identical copies of a random variable distributed according to your probability, your, let's say, forecast probability distribution, P phi. So for people familiar with the continuous ranked probability score, or CRPS, which is widely used in methodology, this is, let's say, a multivariate generalization of the CRPS. Right, so now we want to train generative networks using scoring rules. So what we do is basically just take this, let's say, loss function. So we define the loss function J phi, which is a function of phi, the weights of the neural network, as basically just being the expected scoring rule. So the expectation of Y coming from the real data distribution of the scoring rule between P phi and Y. And if we choose a strictly proper scoring rule, then minimizing this over phi leads you to the correct probability distribution for P phi. Right. So in practice, of course, we don't have access to P star. We only have samples, so we will use this unbiased empirical estimate where we replace the expectation by an empirical mean with samples from P star. And then as I mentioned before, let's say P phi is our generative network. So as I mentioned before, we don't have access to the density of P phi. So we need to somehow estimate the scoring rule as well. So for instance, if we were using the energy score, which I introduced before, we can use an unbiased empirical estimate of the energy score. We can just replace the expectations in the previous slide here by a couple of empirical means. Here we are. So let's say we have we generate samples from P phi, and then we replace the expectations with empirical means. And this is an unbiased estimate of the energy score. Now, the advantage of this is that if you were to basically, let's say, take these estimates, these unbiased estimates of the energy score, you put it back into the unbiased empirical estimate J hat, and then you do the traditional neural network magic. So you compute gradients using automatic differentiation, and then update the weights by simply following the gradients. This is still a valid stochastic gradient descent algorithm for minimizing this function, J phi, on the top of the slide. And this relies basically on swapping an expectation in gradient, as you can imagine, but this basically holds true for most generative neural networks. Right. here I'm showing the two algorithms just to compare how scoring rule minimization and adversarial training differ. So they don't differ too much in a sense. The main differences are the following. So in the adversarial training, you need to have the discriminator network beyond the generated net. Then for sure, you also need to tune like the hyperparameters of the discriminator network, such as the learning rate, let's say. The other difference is, let's say in the training loop, while you loop over training samples, for the scoring rule minimization setting, you have to sample multiple values from your generated network. Because if you look back at the expectation here, you need to have at least 2 samples from P5 for this to be an empirical unbiased estimate. Why in the adversarial setting, the adversarial training, let's say you only need a single sample from P5 for each step of your training loop. But yeah, for the rest, it's basically the same. You do some gradient updates using the learning rate, and yeah, the fact of needing multiple samples seems to be a drawback. But in practice, you get good results even if you use only, let's say, 3 samples at each step. Right. So let's get back to probabilistic forecasting, which is what we want to achieve. And just to introduce some notation. The task of probabilistic forecasting is, let's say, we want to forecast some value y at time step t plus l, given this window of observation. So we have access to observations y from the time t minus k plus 1 up to the time t. So basically here k will be the window length, while l will be the lead time. So like how far in time you want to forecast. So the idea is, okay, what then we use? First of all, we use a generative network to do this, which will be conditional on the previous observation window. And then we compare the realization, whenever we will get that, with the probability forecast, which we get with the generative network. And then we do this kind of sum over a recorded sequence, let's say, and accumulate the scores. So here on the right, you can see a small drawing. So let's say we have an observed recorded sequence. And for a given observation window, we'll use a generative network to generate a bunch of forecasts and use the scoring rule to evaluate how well the forecast was with respect to an observation. Good. So basically, the idea is just to minimize this function over phi. And this will give you some, hopefully good probabilistic forecast, which I'll show you here. It's pretty good in a sense. So I have, we tried this on a few toy examples, including the Lorentz 63 model, which I guess many of you are familiar with. And it is basically a system of three like ODEs. So in this setting, we assume basically to observe only y to introduce some uncertainty, and integrate the model with some schemes. And then we have basically lead time 1, and at each step we have an observation window of 10 of the 10 previous time steps. And I'm showing here a couple of methods. So we have our method with the energy score. Then we have let's say the basic GAN and a more advanced GAN method. So, and the dashed line is the truth, where at each step is the forecast based on the previous 10. Yeah, we have the mean, or actually the median, sorry, and this credible area, 99% credible area. So as you can see here, actually the energy score prediction is much narrower, while the GAN ones are wider. But the interesting bit is that if you look at the calibration error, in most cases, at least for most cases, the energy score has a much lower calibration error. So if you look at this, this vertical, let's say this vertical column here, there are a few cases for GANs where GAN was able to achieve a lower calibration error. But if you look at the performance according to the other two metrics, which are basically deterministic performance measures, then these cases where the GAN achieved a low calibration error are actually very bad according to a deterministic performance point of view. So basically, in a sense, you can think of maybe in this case, the GAN was only forecasting the climatological distribution, but didn't have any performance on a deterministic level. So yeah, and the energy score also gets the best according to the two deterministic performances. And we also moved on to a more challenging problem, which is on a grid, like a spatial grid. And to tackle this, basically, we realized that if you have a fairly large grid, in a sense, the raw energy score is just basically computing a multivariate L2 norm, right? So it discards, in a sense, the spatial structure. So to basically somehow keep the spatial structure, we had this idea of computing patches of, computing the scoring rule on small patches, which we translate. Well, we move around the grid, and then we sum over, which is this this equation. So this is nothing, let's say, super strange. And we apply this to this so-called weather bench dataset, which is basically it is I think it takes the data out of the ECMWF reanalysis data and basically reformats it to be, let's say, easier to handle with neural networks. And here I'm showing you some results. So like on the left, you have GANs, the results with GANs, and on the right, we have the results with the energy score. And the important bit is, let's say, for instance, here, GAN, let's say, if you look at the forecast for GAN, they seem to be fairly nice, but basically they are all the same. So in this case, GAN didn't have any spread, right? While the forecast for which you get with the energy score still seems to be at least, let's say, reasonable, but they are, let's say, different one from the other. And also, if you look at the performance metrics, the same one which I had before, so the here I'm showing three different settings for the energy score, like the energy score computed on the full grid, and the patched energy score with two different patch sizes. And the energy score clearly outperforms GANs and also WGAN GP, which is this more advanced adversarial setting. Yeah. Right. So I think I'm basically done. And just to conclude, scoring rule training is an alternative method to adversarial networks, which is faster, does not suffer from instabilities of mixed max training, so it makes your life much easier, trust me, and it leads to better calibration, at least for the data sets and the models we found. But I believe this holds more broadly. And I've applied it to forecasting, but it can also be applied to other like tasks where you're interested in some probabilistic notion of in some probabilistic uncertainty, such as downscaling or post-processing, as Sebastian was discussing before. Yeah, here is the link to the paper if you are interested in knowing more. Thank you very much.
Thanks. We have time for questions. Perhaps I can start with the question. So you used the energy score as well.
Yeah.
You could also use other multivariate proper scoring rules.
Yes.
So you tried that or a comment?
Yeah. So actually, I lied because I also tried some others in the paper, but I just for the sake of keeping the presentation simple, I only included the energy score. So we also tried the kernel score with a Gaussian kernel, which seems to, well, at least on this case, it works a little bit worse. And we even tried the variogram score, which I think you were mentioning before as well. And that also works fine, but we found that to be much more computationally costly because it's kind of quadratic in complexity with respect to data size. Yeah, you can explore a lot with scoring rules because you can use, let's say, for the kernel score, you can use different kernels, but you could also, like, say, add multiple scores at the same time and do all fancy stuff you wish. So, but we haven't done that for now.
More questions?
Hi, great talk.
Thank you.
Do you have any a sense for like how this, what the spatiotemporal correlations are like in a model like this? Like, so I guess energy score, I think we tend to find in higher dimensions, it perhaps focuses more on the marginals than the correlation structure, right? But because you're training on local patches, maybe that kind of gets around it to an extent.
Yeah, actually, it's a very good question because like these metrics, which I'm mentioning here, they are computing on each single, let's say each single pixel, and then we average it because I couldn't find a way to properly measure the, let's say, how well the structure, like the spatial correlation was maintained. Yeah, like looking at images, it does seem that, let's say, in some cases, at least, yeah, the images you get with GANs are, at least in some cases, a bit more, let's say, knitted, or like they seem to be more physically realistic. But yeah, I guess using the patch energy, especially with lower patches, improves on that a little bit. But yeah, if you have any ideas on how to actually measure the structure, like the spatial correlation structure, that would be super useful.
Yeah, I'm afraid I'm also like unsure how best to measure this, but maybe we can chat afterwards.
Sure, thank you.
More questions? Oh.
So for the energy score, you can use you can choose a beta for the power. How do you choose that?
It just took beta equal 1, I think. But yeah, that's also another like hyperparameter you can play with. Yeah.
Okay, I don't see any more questions.